Welcome friends. In this video we are going to look at the science paper 1 and our focus for now is just some basics about the graphs and science paper 1. Then we'll look at how do you get the information whenever you are given a statement. So let's look at the first one here. So I won't be using the actual graph paper, but what I want and I expecting from you guys is just to get the concept from here. So we have this question: an automobile of mass 2,000 kilograms started from rest. So whenever this word rest is mentioned, this means that our initial velocity is 0. So started from rest position and increased its speed uniformly to 9 meters per second. So this 9 meters per second is our final velocity. When the time was 30 seconds. Then it maintained this speed for another 500 seconds. So how can we answer the first question? Sketch the speed time graph of automobile for the journey described. So let's see how you can do. So what you just have to do here is you get the graph paper given. Then for a question like this, you just have to make your own scale. So from the information, we know that the car started from rest, so we need to have 0. Then the final velocity in the first 9 seconds, in the first 30 seconds was 9. So you put a point in the y-axis, then you say this is where our 9 is, then we'll say speed. So we have our speed, then our time is 30, so we need to plot a point 30,9. So 30,9 is somewhere here. Then you draw a straight line, this. Then what else are we supposed to do? So you need to look at this point here. It maintained this speed for another 500 seconds. So this means that this car moved with the speed of 9 meters per second for 500 seconds. So we are going to have a horizontal line. So at this point here, we are going to have 500 seconds plus this 30. Remember, this 500 is from point A up to point B. So when putting the number here, you just have to make sure you add this. So this was the sketch for this particular question. Then for question B, calculate the uniform acceleration of the automobile. So we know that the acceleration is equal to final velocity minus initial divided by t. So our final velocity is 9 because we can see that the speed did not exceed 9. So final velocity, which is our speed, is 9 minus the initial. This started from 0, then over time, which is 9. So 9 minus 0 is just 9 over 30. So we can now do the math. So I'm getting 0.3 meters per second squared. Then for C, how much force was required to produce this acceleration? So we have the acceleration, then we also have the mass. So which formula are we supposed to use? We are going to use the Newton's second law of motion, which is force is equal to mass multiplied by the acceleration. So the mass is 2,000, then the acceleration is 0.3, which is, if we do the math here, we get 600 newtons as the force. Then D, calculate the distance covered by the automobile when it was moving at constant speed. So the constant speed is at this point here. So we want to find the distance of this. So we can see that this time we have a rectangle, and distance of a rectangle is given by L times B. So the L is this length here. So we know that the difference between 530 and 30 is just 500. Then breadth is this here. So we get it from here, which is 9. So our final answer is 4,500 meters. Then what was the average speed of the automobile for the journey described? So we have the journey for this. Let's find the journey for this shape. So we know that that one has a right angle triangle and can be calculated by this formula. So half the B is just this, which is 30. Then our height is still 9. So 30 divided by 2 will give us 15. 15 times 9, I'm getting 135. So 135 meters was the distance covered at this point. Then for us to find the total distance, we add with 4,500 meters. So my math is giving me 4,635 meters. So this is our total distance, but our final answer will be average speed is equal to total distance 4,635 over total time taken 530. So divided by 530, I'm getting 8.7 meters per second. So this is how we can sketch a graph of a given data. We have another question on radioactivity. So a radioactive element X22398 emits one beta particle followed by 2 beta particles. Then the first question is, what is a beta particle? So we know that the simplest definition that we can assign to a beta is just a moving electron, or it's just the electron, but we say is a particle with one electron. Then B, write the nuclear number and proton number of the remaining nuclide after the two emissions. So let's look at the first emission here. So remember, during the beta decay, the mass number should not change. Then the atomic number must increase by 1 unit. So we'll say this is our Y. Then you write the notation. So that is our first, since we are looking at 2 emissions, so let's look at the second emission. So during the second emission, our Y becomes the daughter, the parent. So do the same. So the mass number should not change. Then the atomic number increase by 1. So 99 plus 1 will give us 100. Z plus C, the notation for beta. So we have 100. Then how can we find the proton number? So proton number after 2 emission is just equal to this number here, which is 100. So there are 100 protons. Then nucleon number is just the mass number. So nucleon number is still the same, which is 223. Then we have a 400 grams radioactive sample, has a half-life of 4 years. Okay, on a graph paper, we need to plot a graph to show this decay curve after a period of 32 years. So let's do this. So we will say so say time in the x-axis. So we need to make coordinates for a question like this one. So mass will be in the y-axis. Now, before the decay, the original mass was 400. Then when time was 0. Then let's look at what was the half-life. So the half-life was 4 years. So this means that after 4 years, half of the sample must decay. So after 4 years, half of this. So you do 400, you divide by 2 will give you 200. So 200 remained. Then after another 4 years, which is 8 years, half will decay. So this will give us 100. Then after another 4 years, half will decay. This will give us 50. Then after another 4 years, half will decay. This will give us 25. After another 4 years, which is 20, half will decay. We get 12.5. Then after another 4 years, half will decay. So 12.5 divided by 2 should be 6.25. Then we have 28 here. So we divide again by 2. So 3.125 remained. Then if we add 4 years, we get 32. So we are going to end at 32 because this is what they need. So if you divide by 2, you get 1.5625. So after you have this information, then you can make your graph. So in x-axis, you just have to make sure that you use the scale of 2 centimeters to represent 4 units. So 80, 12, 16, 20, 24, 28, then 32. Then what else are we supposed to do? We go in the y-axis. So in the y-axis, you just have to look at the numbers. So with a graph paper, you can use the 2 centimeters to represent 50 or 100. You still get the answer. So just say 50. So let's say 50, 100, 150, 200, 250, 300, 350, then 400. So the first one is 0.4, 400 is here. The second one 4,200 somewhere here. Then 8,100, 12,50, 16,25, 20. So something like this. So the graph is coming closer to the x-axis. So this is the shape of the graph that is expected, but for using the actual graph paper, make sure it has to be neat. So that is the concept. So the concept is whenever you are given this data, make the coordinates. Then after that, you look at the other question. So what period of time would it take for the sample to reduce to 40 grams? So 40 grams, mass is in the y-axis. So this is where our mass is. So you need to go in the y-axis where there is 40. So 40 is somewhere here. So you draw a horizontal line. So according to my predictions here, the time should be, this should be 14 years. Then name a source of gamma radiation. Source of gamma radiation can be nuclear explosions. So another question, a car travels along a straight road. The speedometer readings every after 5 seconds are shown in table C 1.1 below. Okay, then draw a velocity time graph to show the changes of velocity with time. So we have been given the coordinates here. So let's see what we can do. So the same, you need to draw the XY plane on a given graph paper. Then we need to come up with the scale. Now in the x-axis you put time, and according to our data, time is in seconds. Then here we put velocity, which is in meters per second. Now the numbers all the time we have 0, 5, 10, 15. So whenever you have numbers like this where they have a certain sequence, the addition of 5, you just have to say 2 centimeters to represent 5 units. So if this is 0, you put your 5 here. Then 10, 15, 20, 25, 30, 35, then our 40. So let's check. Okay, yes. So then for velocity, we can see that the lowest number is 0, then the highest number is just 30. So you can just say 2 centimeters to represent 5. 5 can fit on a graph paper. Or you can say 2 centimeters to represent 10, 20, 30 here. Excuse me. So the first pair of coordinates we know is 0, 0. So 0, 0 is here. Then the second one, 5, 10. So 5, 10 is here. Then 10, 20. So 10, 20 is somewhere here. 15, 30. 15, 30 is here. Then 20, 30. So 20, 30. So we can see that now this time velocity is not changing. It means the car is moving at a constant velocity. So 25, 30. 30, 30. Then what else? 35, 15. So we can say that now it is reducing. Then the last one is 40, 0. So for you, I expect you get a straight line for a graph like this. So this is our first question. Then be using your graph, determine the distance covered after 20 seconds. So 20 seconds is just here. What shape are we forming? So the shape that we are forming here is a trapezium, and this is our A. Then the distance below, this is our B. So say distance is equal to half a plus b multiplied by h, which is half our a. We just have to move this. So the a is just the difference between 20 and 15, which is 5 plus our b. You just have to get the 20, the time mentioned. Then our height is 30. The height is this distance from 0 up to here. So 20 plus 5 will give us 25. Then 2 here is 1, 2 here is 15. So what is 15 times 25? So I'm getting 75 meters. Then for Roman number 2, total distance traveled by the car. So total distance traveled, we are going to use the same formula. Distance is equal to half a plus b times height. Now this time our a is this distance up to here. So if we move in the x-axis, we are going to find the difference between 15 and 30, which is just 15. So you subtract plus the b. We are told total distance, so the b is where the graph is ending. You just get 40. So plus 40. Then our height is still 30. So 40 plus 15 will give us 55. 2 here is 1, 2 here is 15. So what is 15 times 55? So I'm getting 825 meters as my total distance. Then Roman number 3, average velocity is equal to total displacement or total distance, which is 825 over total time taken, which is 40. So if you divide by 40, you get 20.6 meters per second. So this is how we can simplify a question like this one. Okay, so now we have another question. A gear counter was used to measure the activity in count rates per minute from a radioactive sample in the laboratory over a period of years. Over this period, the background radiation was regularly measured at 4 counts per minute. The table of results is shown below. Okay, the question, copy in your answer booklet and complete the table, giving the activity of the sample alone. So we can see that the time, this is our time, then this will be our y. Because the question is on Roman number 4, on a graph paper, plot a graph of the values of the activity of the sample against time. So now we can see that the row for time is fully filled. Recorded activity in counts per minute is also fully filled. Then we can see that there are some spaces where we are supposed to fill the activity due to the sample. So for this one, first let's look at the background radiation. So the background radiation is 4 counts per minute. So this number is very important. So 4 counts per minute is what we are going to use. So whenever you are trying to find the activity due to the sample, so it's like this. So you get this number, which is 124. So 124 minus the background, which is 4, will give us 120. Then we have 8 minus 4. We are going to get 76. So the pattern is you subtract the background radiation. So here we have 48. 34 minus 4, we get 30. Here we have 19. Here 12. Then 12 minus 4, we get 8. So that's how you complete. So whenever you're given a background radiation and recorded activity, for you to find the activity due to sample alone, you just have to subtract the background. Then what is background? So background is defined as this is a small amount of radiation, a small amount of radiation, a small amount of radiation present on Earth at all time. Then give two possible sources of background radiation. So we have radon gas, then we have cosmic rays, so apart from cosmic rays, also foods, then building, all these are sources of background radiation. Background radiation, we are just looking at a small amount of radiation that are present on Earth at all times. Then we have this question: on a graph paper, plot a graph of the values of the activity of the sample against time. So you do the same. You draw the XY plane on your graph. Then you need to look at which value will be in the y-axis. So if you look at this against so it's the activity of the sample alone against time. So whatever that comes before against is in y-axis. So say activity of the sample alone. Then in the x-axis we get our time. Now let's look at which scale are we going to use. So let's look at in the x-axis, it's just direct. We just say 2 centimeters represent 1 unit. So 2 centimeters represent 1 unit. So say 1, 2, 3, 4, 5, 6. What of the y-axis? So y-axis, where the lowest number is 8, then the highest number is 20. So we can just say 2 centimeters represent 20. So say 20 here, 40, 60, 80, 100, 120. Then from there you start your graphing. So the first one is 0,120. 0,120 is just here on the y-axis. The second one, 1,76. So 1,76. So 1,76. I'm just trying to make it as clear as possible, but I'm not using a graph paper, so it's somewhere here. Somewhere here. Then the other one, 2,48. 2,48. So 40 is here, 48 is somewhere here. Then 3,30. 3,30 here. Then 4,19. 4,19. 5,12. 6,8, almost here. So this is the graph that you can draw from the given information. Then let's look at from the graph, determine the half-life of the substance. So you just get the concept. So it's half times the original number from the y-axis, which is sample. So it's half times the highest number is 120. So we get 120. Half of 120 will give us 60. Then we need to go where there is 60. So we go, we do this. So you move. So my prediction half-life is giving me almost 1.5 years. So you just have to get the concept here. Okay, so we have another question. A spring with its upper end fixed hangs vertically alongside a meter rule. The lower end of the spring gave the following readings in table C1.1 when various masses were hung from it. Okay. Then the first one, state Hooke's law. So Hooke's law states that the extension of a material is directly proportional to the force that is stretching it. So say the extension Okay, so this means that if the extension, I mean the extension and the force are directly related to each other. So if you increase the force, the extension will also increase. Now, how do we fill in a table like this one? So let's first get the concept here. So let's say this is our original spring before a weight is hung. Then let's look at the reading here. So the reading before the weight is hung, the reading is just 10. So 10.0 is our original length of the spring. Now, where are we getting the first zeros? So here we can see that before any mass was hung, the applied force is 0. Then the extension will also be 0 because nothing has been extended. Now we move to this point. So now this time let's look at if we now hang a substance with a mass of 0.02 kg. So what is the applied force? So remember, the applied force is just the weight, which is weight is equal to mass times gravity. So this mass here, you multiply by 10. So 0.02 times 10, you get 0.2. So that will be our applied force. Then what was the reading? So after a certain weight is hung, the spring extended a bit. So extended a bit. Now this time the length is, we can see we have 12 centimeters. Remember, the original length of the spring is 10.0. Then after this is hung, then we can see that the spring extended to 12 centimeters. So the extension is just the difference between these two numbers. So we just say 12 minus 10. So the key point is these numbers here will be subtracting by the original. So 12 minus 10 will give us 2. So the extension is 2 centimeters. Let's just say 2. Then the second one, we have 0.04. Then 0.04 times 10, we get 0.4 as our force. Then the extension is 14. So what is our extension? So 14 minus 10 is just 4. we go at this point 0.06 times 10, which is 0.6. Then 16 minus 10, we get our 6 here. Then 0.08 times 10, 0.8. Then here we are going to have 7. So here we can see, so these values are found by just calculating the weight of these numbers here. So that's how we are getting this. Then these values are found by the reading. You get the reading in centimeter, then you subtract these increasing numbers. So like 12, 14, 16, so you subtract 10. So that's a picture that we are getting here. So we have done the first one. Copy and complete the table for the values of applied force and extension. Then draw a graph of applied force against extension on a graph paper. So you do the same. So you draw the XY plane. So you need to come up with your own scale. Remember, questions like this differs. That's why you may find out that maybe your friend or your neighbor is using a scale of 2 centimeters represent 5, the other one 2 centimeters represent 10. That's not an issue. So draw a graph of applied force. So applied force will be here. So applied force. Then against the extension. So our extension will be here. Now the extension, so the extension is in the x-axis. So the extension is 0 up to 7. So how can we use these numbers? So we can say 2 centimeter. So 2 centimeter to represent 2 units. 4, 6, 8. Front we can reach up to 10. Then applied force. So applied force, we can see that we have 0 up to 1. 0 up to 1. So say 2 centimeters to represent 0.1. So let's hope you have got the concept by now for this question. So I'll just say 1 here. So let's look at the first one. So the first one is 0, 0, okay, so 0, is just the origin. And the second one 2, 0.2, somewhere here. The second one we have 4, 0.4, somewhere here. Then we are going to have 6, 0.6, so 6, 0.6 somewhere here. Then 7, 0.8, so 7 is somewhere here. 0.8 is somewhere here. Then 7.5, 1.0 is somewhere here. So the concept behind the Hooke's law is that there should be some points that should give you a straight line. So we need to have a straight line. Then the last 2 points can give you a curve that is not straight. And there is an explanation for this. So how do you know that we need to have at least some points that should be giving us a straight line? The concept is just this. Since we have said the force is directly proportional to the extension, so whenever you have a directly proportional relationship between two variables, you are expecting to have a straight line. Now, why is this line bending. So if you have a spring, then if you add some weight, it will reach at a point where this spring will stop extending. So at this point, let's say if the weight force is equal to, let's say, 10 newtons, then the spring is also, remember, the weight force is bringing down. The spring also is exerting the force, which is trying to, the spring is trying to go back to its original point. So whenever these two forces equal to each, then the spring will stop to extend. And this force, we call it restoring force. So whenever the restoring force is equal to the weight force, or the force that is bringing down, then we have reached what we call elastic limit. So elastic limit is just a point where the spring cannot stretch. So how do you tell from the graph? So we can say on the graph, show the elastic limit. So this is our elastic limit. So that is just what you have to know. Then sometimes you may be given a question like this and asked, did the graph reach its elastic limit? Did the spring reach its elastic limit? So if you just have a linear line, a straight line, then the conclusion is it did not reach its elastic limit. For you to know that it reached its elastic limit until there is a point where at least is bending. Then what else can you be asked? So the other thing that you can be asked is, let's see if we can write the equation. So we know that force is directly proportional to E. So if we remove this, we put K, we have KE. So over E over E. So if the question find the constant of extension, K is equal to the force over extension. Okay, so let's say we get maybe 2 points. So the first 2 points, extension is 2, the force is 0.2. So let's say 0.2 over 2. So 0.2 divided by 2, you get 0.1. So 0.1 as our constant. Let's say we get 4 by 0.4. So 0.4 divided by 4, you get 0.1. Then 6 divided by 0.6 divided by 6, you still get 0.1. That's why we call this one as the constant. It has to give you same numbers. Now at elastic limit, it may give you values different from these values, because at this point the spring has stopped extending. Okay, so then the other thing that you just have to have in mind is that when it comes to graphs in science, expect any topic to be under graphing. So electricity also comes in graphing. So the whole thing is just about the concept. So whether you are given electricity, whether you are given, sometimes even the refractive index, you may be given values and asked to make a graph. Then from there you just have to make some interpretation. So the interpretations that we make, if let's say we are dealing with the electricity, remember you may encounter electricity. Since we all know we have at least some key points when plotting. So the interpretation is that if the graph gives you a straight line, whatever that you have in the y-axis is directly proportional to whatever you have in the x-axis. So that's a relationship, that's an interpretation. Now if you plot a graph, then maybe a graph is not straight like this, then it's not directly proportional. Then if you draw a graph and you have something like this, then this means that you are dealing with inversely proportion, where one value is increasing, the other value is decreasing. So that's the point. So you can be asked to make a graph of electricity, then to make a graph of temperature. I've seen a question where they give you temperature. I've seen a question where they give you to about potential energy. You draw a graph. So what you just have to know is how do you plot a graph, how to make your own scale, then how do you interpret whenever a graph is like that. So if this is, let's say we have voltage in our y-axis and current, so the interpretation we're saying is voltage is directly proportional. Then if you have a graph like this one and ask, did the graph obey Ohm's law, then we can say yes, it obeyed the Ohm's law. Why? Because we have a straight line. So under electricity, whenever you have a straight line, then you are dealing with the Ohm's law. Then a substance or an element, whatever substance that you are using, is an ohmic. So you may encounter this language is an ohmic. So if it is an ohmic, it has to obey Ohm's law. If it has obeyed Ohm's law, then you need to have a linear graph. Then the other calculations that you may ask is, maybe you are given current. If this is 2 amps, what is the voltage? So you do the same, just draw a line like this, then you turn here. So at this point is where you are expected to get your answer. Then lastly, what I can advise you is also to work on conversion. So there are some conversion that you need to look at away from the graphs, like how to convert from mass to grams and vice versa, then kilometers to meters, millimeters to meters, stuff like that. So that's it for this video. Thanks for watching.